and welcome to 17.3 Local Temperature Variations. There is one vocabulary term which we will hit on later in this session. If you have not gotten that vocabulary term in your lab notebook or the definition, and if you have not skimmed through the section, please do so at this time. Our objectives include identify the factors that cause the intensity of insolation to vary from place to place, describe how the characteristics of a material affect its rate of solar absorption, and analyze a temperature map. Hope you've enjoyed the first two sections. Now, intensity of insolation varies from place to place because insolation heats Earth's surface and atmosphere unequally. Now, if you remember, insolation is the energy coming from the sun. It travels in radiation, conduction, and convection. It moves through the system. And the factors that influence the intensity of insolation include the angle of insolation, time of day, the latitude, time of year, and the characteristics of a material. Now, if we look at the diagram for angle of insolation, this shows when sunlight hits Earth's surface at an angle, its energy is spread over a greater area, so the insolation is less. The angle of sunlight varies with time of day, latitude, and time of year. Now, with the two different descriptions, we see that light is most concentrated from an overhead source at a 90-degree angle. So when the sun is directly overhead, the angle of insolation is 90 degrees, and Earth's surface receives the maximum amount of energy. Now, as the angle of insolation decreases, the energy of the rays is spread out over a larger area. So the energy per unit area decreases. So light hitting at an angle is less concentrated. So what happens when the angle of insolation changes? Sunlight is spread over a larger area and the intensity of insolation decreases. Now, the intensity of insolation depends upon the angle at which sunlight strikes Earth's surface. The intensity is greatest at low latitudes near the equator during the summer and around noon. Now, during the time of day, because the sun's rays are closest to the vertical at noon, the intensity of insolation is greatest at noon. The highest temperature, though, is generally not at noon. Instead, it's usually in the afternoon. And for several hours after noon, the low atmosphere receives more heat from the ground than it loses. So the temperature keeps rising until well into the afternoon. The coldest hour usually comes just before sunrise because the ground and the lower air lose all the heat through the night. With latitude, because Earth is spherical, the sun's rays strike the surface anywhere between 0 and 90 degrees. So these areas, if you're near the equator, it's almost vertical rays for the entire year. So they have hot climates. In the higher latitudes, which means near the poles near 90 degrees, the sun's rays generally strike the surface at a low angle. So these areas may even have no sunlight at all for some parts of the year and are usually cold year-round. Now, if you're looking at this diagram here, on June 21st, you can see New Orleans is at a direct angle for Earth's insolation. And then December 21st, the angle changes and the intensity decreases. So the angle of sunlight varies with latitude. For the time of year, locations in the middle latitudes like the United States get near vertical rays in the summer, so the summers are hot. The angle of the sun is less vertical in the winter, so the middle latitudes are cold. So if you're looking at this diagram, New Orleans obviously would be hotter on June 21st and cooler on December 21st. An isotherm is a line drawn on a weather map through places having the same atmospheric temperature at a given time. Now, a marine chart from the late 1500s contained isobaths, which are lines of equal depth, typically with the ocean, correlated with the ocean. Now, isotherms were not introduced until 1817 by a German scientist named Humboldt. Then a professor named Brandes used isobars, lines of equal pressure on a weather map. All three assist in reading meteorological patterns. Now, here are two examples of a weather map looking for meteorological patterns. Now, cloud cover can affect how much energy moves through the atmosphere. Land heats and cools more readily than water. Isotherms shift with the seasons more dramatically over land than over water. Now, the intensity of insolation that reaches Earth's surface depends not only on the angle, but also on how much energy makes it through the atmosphere without being absorbed, reflected, or scattered back into space. Clouds reflect a significant amount of insolation back into space. More solar energy reaches Earth's surface on clear days than on cloudy days. More radiation travels through Earth's surface out to space on clear nights than on cloudy nights. So the question is, why does the temperature of land vary more than the temperature of water? The reason is that water and land warm up and cool off at different rates. Water warms much slowly than land for many reasons. Now, heat energy from insolation spreads through a greater depth in water than on land. Now, on land, insolation warms on the top few centimeters of the soil, but the sun's rays penetrate to a depth of many meters in the water. Now, water spreads heat easily by convection because it's a fluid. Now, in water, some solar energy is used in the process of evaporation. Therefore, less solar energy is available to raise the temperature of the water. These are some of the concepts that we'll also use in the lab: absorption and radiation of energy. Now, the maps on this page show mean or average temperatures in Asia and Australia for January and July. Notice the warmest temperatures are to the south of the equator in January, right here, and to the north of the equator in July, right here. The sun's rays are more vertical north of the equator in July. And notice also that the warmest and coldest temperatures are over land. Land heats and cools more readily than water. So the continents are warmer than nearby oceans in the summer and colder than the nearby oceans in the winter. So, which surface is likely to be hotter on a sunny day? A parking lot surfaced with blacktop asphalt, or one surface with crushed white gravel? If you answer the blacktop, you are correct. It absorbs more solar radiation or insolation, so it would be the hotter surface. The white gravel would reflect some of the insolation. Again, another concept we will learn in the lab. We are done with 17.3. Please look at the section review questions 1 through 7 to help gauge your understanding of the concepts. And if you have any troubles, please ask the instructor.